Muchas gracias. Es un placer estar aquí en Cuernavaca. No predico, no hablo en español. Dice mi colega Susana Martínez Conde que hablar mañana a mí todas estas palabras para mí, porque no hablo, dice a mí, gringo, no. Junkie cabrón. Mira, habla esta palabra sin nada más y después en inglés. Voy, okay. So, is there a way to make my screen the only screen? If it is, that'd be great. Okay. So, what I'm going to talk about is at the other end of the spectrum from what Susan talked about today. Where I'm going to talk about the nuts and bolts of vision, and that by understanding those nuts and bolts and the nuts and bolts of neuroscience, we can potentially restore vision with prosthetic means. And I don't mean stimulating the brain in such a way with electrodes that someone who's blind could have phosphenes. I mean replacing vision so that they can see with 20/20 vision. Okay, that is the goal here. And so this is it's a theory about how one could do it, and then it's kind of a report of where we are in the process of doing that. Okay, so first you need to understand a couple different premises here, okay? So first off, visual perception is a thumbnail sketch. Now what I mean by that is this. I want you to all put your arms out with your elbows straight and look at your thumbnail, okay? Now, while you're looking at your thumbnail is the only thing in your visual field that is in 20/20 vision, okay? Everywhere else, you are legally blind. Your vision is less than 2200, everywhere else. So the only place you can see, the only place you have ever seen, the only place you will ever see is the size of your thumbnail at arm's length, okay? Approximately 1 degree, maybe a little more, okay? Square. That's less than 0.01% of your visual field. So it's 1/1000th of your visual field, more or less. Okay, so the good news is that to replace vision in a fulsome way, to replace 20/20 vision, we don't need to replace the visual field. We need to replace 1/1000th of the visual field, because that's what you're doing now, right? So when you walked into this room, you could only see with that tiny bit. So how is it possible that you can see at all? Okay, and the answer is you make 1 to 3 eye movements a second. Okay, so when you walked into this room, you walked around and you found your seat, and nobody fell over, nobody ran into each other accidentally. It's a biological miracle that this works, but you basically, over the course of the seconds it took you to get from the door to seat, made between 10 and 30 eye movements, and you saw 10 to 30 square areas, square degrees of this 1200 square degree visual field, okay? And so with less than 1% of understanding what the room actually could possibly look like, because you were blind everywhere else, you built a model in your mind about what you could see, which we call consciousness, and you use that to navigate to where your seat is and sat down. So how do we make a prosthetic do that? And the answer is we don't need to make a prosthetic do that. All we need to do is need the vision where information is at its sparsest, least represented state, and replace that. Because then from going down the pathway of neuroscientific knowledge from there that the brain has, it will take that information and build the model of consciousness itself. We don't need to solve that problem. We just need to replace the information and be clever about where we do it. Okay? So how can we go further from here? As I said, we need to fix the fovea. The fovea is what we call the part of the retina that has this size of about a thumbnail at arm's length. And if we fail to fix it, you still have blindness. And this is, I want to say, what's important here, because everything everybody's done so far with prosthetics and vision, okay? has not addressed the fovea. It's certainly not addressed the fovea at its full resolution, okay? So therefore, none of the prosthetic approaches to date could ever work to restore vision, okay? So now another premise that we need to discuss is the stars. Now, here in Mexico, maybe not in Mexico City and Cuernavaca, but if you go a little further out of town, you have a beautiful, clear night sky. And if you look up in the night sky, the dimmest star in the sky represents the smallest thing your visual system can see. It is the unit, the smallest unit of vision, okay? So you see dim stars and you see bright stars. And what's interesting here is that, do you know the difference between the smallest star in the sky and the biggest star in the sky? Anybody want to take a guess?
The light
What do you mean the light?
that we receive about the star.
Yes, so the light's different, but in what way is it different?
Will it have more?
It has more, that's exactly right. So the difference isn't the size of the stars. There is no difference in size in the stars. All the stars are so far away, no matter how big they are, they're smaller than one photoreceptor area in your retina. None of them are bigger than one photoreceptor. So how can it be that some stars look bigger than others? It can only be that some of those stars have so much light coming to your eye that the entoptic spread of that light within your eye, it basically scatters and causes multiple photoreceptors to activate through noise. Basically a noise process, reflecting off the back of the retina, inside the eye itself it scatters, the lens scatters it, and more than that, the atmosphere itself, okay? So that is the difference between the dimmest and the smallest star in the sky, but what this means is that the dimmest star in the sky is the smallest thing you could possibly see. And so if we can make a prosthetic that can replicate the dimmest star in the sky and a pattern of those, we've done it. That's the job. Once we can do that, we can restore vision. Okay, so that's the theory I'm trying to solve. Now, star sizes differ due to scatter. Prosthetic stars would be the building blocks of everything. Okay, so let's make a prosthetic star. How are we going to do it? All right, let's talk about how normal vision works. The neural impulses that travel through the optic nerve to the lateral geniculate nucleus of the thalamus. These signals then travel further through the optic radiations into the primary visual cortex, V1. In the layer 4 of the nucleus V1, where the retinotopic interns, on and off stars are arranged perpendicularly to that light. Oh. Did that work? No. I gotta keep pushing this button until it turns off. I can't mute it from here.
Yeah, it's muted.
Oh, you did it. Magic touch. Okay, so light enters the eye. It gets transduced into electrochemical signals in the retina that translate into the optic nerves through the retina, goes to the lateral geniculate nucleus of the thalamus, where it's split into, it stays split into left and right eyes for one half of the visual field versus the other, and then it travels up to V1, and this is the input layer that we're representing here as a model, okay? So we now know, since 2016, how the inputs from the thalamus into the visual cortex work. And this is the only place in the brain that we know this. We know nothing about the pattern of anywhere else into the cortex from the thalamus anywhere. We could only solve this in the visual system with our current knowledge, okay? And what we know since 2016 is that if you look at this being I took my down actually. That region right there, okay, represent a square millimeter of cortex of the input layers, and it's split into two eyes. So the red is one half, one eye, and the blue is from the other eye. And each eye has split into halves for on cells and off cells. And so by comparing the inputs from on cells that like to see the stars against the black sky versus the off cells that like to see little black dots on white pieces of paper, by comparing the inputs at that given point in space, you get contrast. And that's how contrast works. Now, there's another couple dimensions I'm ignoring here, like color, but it's, in a sense, first off, we know less about it, and secondly, it's a bit of a trivial problem once you solve this. So we're just going to talk about this one aspect, okay? But this explains these four quadrants of what comes into a given hypercolumn, and this hypercolumn explains every single thing about vision in that point in space. There's nothing left after that. So if we could replace those inputs into the visual cortex, we've done it, okay? That's it. Everything else, the brain takes that information and runs with it. So we don't need to prosthetically address anything else, with one small exception that I'll talk about later, okay? So how do we make a system that we can stimulate from a camera and stimulate those four quadrants of the hypercolumn inputs, okay? Now I want to ask if there's any questions about what a hypercolumn is or anything I said before. I know that the movie got a little garbled there because it's really important that we understand it. Yeah.
Roughly how many hypercolumns are we talking about there?
There's approximately 1,200. Okay, and I want to talk a little bit about that. 1,200, okay? Yeah.
How many robots are in one of the white ones and the black ones more or less, or is it one?
A cubic milliliter of cortex is approximately, I believe, 100,000 neurons.
Stimulate the half of these 100,000.
Something like that, but not really. So what's really happening is what we need to stimulate are the inputs from the LGN, and there's approximately between 25 and 200 neural inputs from the LGN for each of these things. It's almost certainly on the 12 to 25 side. Okay, so the point here is Susan's question is really important. There's 1,200 hypercolumns for the entire visual field. 1,200. Let's talk about the fact that
Motion gets processed out of these two.
Yeah, so this input there's no motion sensitive cells up to this point. There's no stereo cells. They're all monocular cells up to this point, and there's no motion sensitivity, okay? So everything that arrives here is just center surround on-off cells. That's it. Everything else is built in the cortex from those, okay? So if we can replace those, that's it. We did it. Okay, that's the theory. Now, with 1,200 hypercolumns, that means that we can only see 1,200 areas of the visual field. Do you feel like you see 1,200? I mean, this has 12 megapixels, and it still takes crappy pictures, okay? How is it possible that with 1,200 pixels that we see so much? And the answer is, that's a problem for someone else. I don't need to solve that problem. I just got to solve not just the hypercolumn, not 1,200 hypercolumns. I don't need to solve 1,200 hypercolumns. 2/3 of those, or about half, say 2/3 to half of those, are for the periphery. I'm not solving the periphery. I just need to solve the fovea. Now, of those 1,200, 300 to 400 of those hypercolumns are for the fovea. Okay? Most of, or a third to a half or so, of primary visual cortex is dedicated to the fovea of the macula. Okay, and that's what we need to solve. We're not solving anything else. So if we can stimulate that region, okay, which is essentially 20 by 20 hypercolumns, okay, that's 400 hypercolumns, right? Now we're talking about real, like this problem, you know, in theory, if you do this, problem isn't so huge, right? We basically got to be able to stimulate 4 by 4 differentially, independently, area of the brain, times 20 times 20. That's it, okay? So we need a 1 centimeter by 1 centimeter chip that can somehow stimulate those things. Now here's the problem. Electrodes aren't going to work. That's, I think, the fundamental problem. That I'm an electrophysiologist, I love electrodes. However, electrodes are limited in stimulation. I think this is something that Elon Musk is learning, okay? Of all the electrodes in the world, in my opinion, and as a physiologist, we all have different opinions about electrodes, okay? In my opinion, Elon Musk's electrodes are the most beautiful electrical devices I've ever seen. They're amazing. He's even got robots to put them in because they're fun. You put them in and put them around blood vessels and just thread them right where you want. The tips of those things are less than 5 microns, okay? That's 6 times smaller than a pyramidal cell. So you think, wow, these things are really precise. If we could put in 100,000, or you could really get down to the brass tacks. But the answer is that's just not true. If you put in 100,000, first off, you'd ruin everything. You can't do it. You can only put in at most 1 per hypercolumn, or maybe a couple. Okay, but worse than that is that even with a small electrode tip, to stimulate a cell, you need enough of an electric field to actually overcome the thresholds of the channels in those cells and cause an action potential, okay? To do that, you create an electrical field that's 100 microns wide, as he's discovering, okay? So 100 microns in either directions is 200 microns wide, okay? 100 micron radius is 200 microns wide. So now, this model assumes you have synaptic precision from the LGN. Synapses, boutons from the LGN come into V1, and they are about 1 micron in size, okay? That's your spatial resolution of the inputs into V1, 1 micron in size, okay? If you use the finest electrodes in the world, and I believe they might be the finest electrodes you could ever have, okay? You're going to get a precision that's 100 microns in radius in a sphere. It's over 1 million times lower resolution. Okay? You're stimulating not just the synapse you want to stimulate, you're stimulating all of the synapses on the wrong side of all of these different borders. In the wrong hypercolumn, in the wrong eye, in the black and white, and it's worse than that. Every single one of these cells has an inhibitory cell next to it that keeps it from becoming epileptic. That's the fundamental role of inhibitory cells in the brain, is to stop the excitatory cells from going epileptic. And when there's just a tiny little problem with your GABA channels, you are epileptic, okay? So we need those, okay? But with this electrodes, we're going to stimulate the excitatory and the inhibitory cells at the same time. And what we've shown is that in theory, you can get at best 3% compared to what you get with a natural input, okay? And you're going to get a phosphene instead of precise. You're not going to get 20/20 vision. It will never work. The claims of Neuralink that they're going to restore vision is false. It can't possibly work. I do not believe it's even worth pursuing. Here's why it's not worth pursuing. You may say, well, it might help some people. Well, okay. Let's talk about if you're putting an implant in the eyeball, okay? You got a blind person, their eyes don't work, okay? You put an implant in their eyeball and you give them some vision with that, maybe enough to get a Zeitgeber when they wake up in the morning to reset their clock. Maybe they can see a doorway in front of them. Maybe there's some small benefit. I think that's okay because the cost is very low. Their eyes didn't work anyway, okay? What's going to happen is after 10 years, there's going to be gliosis. The electrodes are going to get covered in stuff. It's going to stop functioning, okay? This happened, 10 years would be a very long horizon for one of these things. And when you pull them out, the gliosis is scar tissue. You pull it out, you've ruined the tissue. It's never, you no longer have an eyeball, okay, when you pull it out. And you have to pull it out at the end because it goes from being a somewhat beneficial device to being a completely non-beneficial device that is a source of potential infection, etc. Anyway, so you have to take it out at the end. And what you've done is you've had an eyeball that didn't work, you gave it a little function, and then it doesn't work again. Actually, that's a net gain. Okay, I like retinal implants, no problem. But now you're talking about the brain. Now you're going to crack open someone's skull, you're going to stick a bunch of electrodes in there, they're eventually going to have gliosis, they're going to form a scar, you're going to go in after 10 years when the thing stops working because there's no resistance around the electrodes anymore because the scar's filled with salt water and you can't stimulate anymore. You pull this thing out, you've just pulled out their primary visual cortex. They're blind forever, no matter what you want to do, okay? And for what? right? For having a bunch of phosphines in the periphery, which is what you want, because that's the only put the electrodes. You can't even put them in the fovea. I think it's unethical. I don't think you should do it. Until you have a theory where you can restore vision to the point by putting an implant in the cortex, where you actually restore vision in the fovea, at least close to 20/20, so someone can have a quality of life where they can see their grandchild's face or, something to that level, you shouldn't do it, okay? This theory, I hope, would do it. That's why I'm saying we should pursue this further. Okay, how do you do it then? Okay, I just told you that my entire career based on electrodes is going to fail. All right, so let's talk about that there's no current therapy that restores high acuity foveal vision due to catastrophic damage in the eye, the brain, it doesn't matter where, okay? The optic nerve, it doesn't matter, okay? There's nothing that restores foveal vision at all, okay? So there's more than 200 million patients right now who suffer from foveal vision loss in the world, okay? That's 3 to 5% of the world, okay? So the stakes are big, okay? This is mostly macular degeneration patients. AMD is the most common form of blindness in senescence. About half of us eventually, if we're lucky to live long enough, we're going to end up with AMD, okay? Traumatic ocular injury, glaucoma, diabetic retinopathy, a bunch of stuff I haven't even listed here makes this number higher, not lower, okay? So how can we get at this? So first off, how do you deal with anterior segment damage? Well, that's good. Anterior segment, in case you don't know, is when your lens or your cornea of your eyeball, the actual physical eyeball that moves around, is broken. Okay? So ophthalmologists are really good at fixing anterior segment. Not so good at fixing retinas, because that's really brain surgery. Okay? And terrible at fixing anything inside the brain after you leave the eyeball. Okay? So we really can't do anything besides that. Okay? So with photoreceptor damage and anterior...
Anterior segment, you mean like the cornea? Or
Yeah.
Okay.
Yeah, exactly. So ocular damage in the eyeball involving the lenses. Okay? So to fix that, to fix either of these problems, photoreceptor damage in the retina or anterior segment damage, you can use retinal implants. Okay? Now, with retinal ganglion cell damage, which is the cells in the retina that actually send axons in, become the optic nerve, they surround the brain. There's nothing you can do with current technologies, okay, except cortical implants, none of which are on the market now. Okay, none of them actually made it before they went out of business. Because why? Honestly, I'm pretty sure the FDA. I don't know exactly why. They don't tell us, but I'm pretty sure the FDA went, "Are we sure we want to do this? Right? Is it really going to help anybody to have a bunch of noisy glitter in the periphery of someone's vision after getting a major neurosurgery for something you're just going to have to pull out and completely destroy that piece of tissue?" Okay? That's what I would be concerned with. I doubt it's ever going to happen, honestly. Okay, so, but with an optogenetic system, like I'm going to show you, optogenetic brain system, the one that we're proposing, we think that it'll address all of these problems, and by doing precise spatiotemporal cortical activation of on-off channels, like I showed you before, okay, what this means is what I told you before, we think we can optimize visual restoration by giving the highest attainable visuality, the maximal contrast sensitivity, full stereoscopic activation, and address the fact that the person needs to move their eyeballs to actually see. Okay? So how are we going to address all of those things? Here's the general overview, of which I'll go over the details afterwards. But this movie kind of shows the general idea. Okay? I need to turn on the mic or the sound. Okay, here we go. To restore the visual pathway of the person that we're blind, we must develop technology Does everybody understand? I don't know how Chitty did it. There it is. I got it.
There is.
I don't know why I did this one. Anyway, these neurons are the neurons from the LGN coming in, okay? So we've made the LGN neurons into photoreceptors. They're sensitive to light now, okay? So if you shine light on them, they light up. But how do you shine light on them that is precise at the level of the hypercolumn? The answer is the boutons are also sensitive to light, and they're laid out in the hypercolumn map on the surface of the cortex in V1. It's just laying there for us to stimulate, right there on the surface. All we have to do is put a video projector in a tiny little implant in the brain and shine very precisely on those hypercolumns. Those hypercolumns are 1 millimeter big. 1 millimeter, that's huge. It's huge, okay? These pixels are in the micron size. They're, a very big, very cheap, very inexpensive pixel, okay, for a phone, right? Would be like 11 microns. Okay, that's inexpensive tech, that's cheap, okay? Talk one of these retina displays. This retina display has way more resolution than we need for that implant, okay? To stimulate just one of those tiny little quadrants of the hypercolumn. If we stimulate it from there, we're going to light up all of the neurons in that quad of the hypercolumn, and those boutons are all the same kind of input. It's at the resolution of vision. It's either the on or the off, or left or right eye. And if we now say had 4 pixels, one for each of those quadrants, now we could stimulate and just do the spatiotemporal patterning, and it would completely restore vision, okay? Now, I'm making it sound very easy, okay? But in theory, it's easy, okay? In practice, the engineering is where things get tricky, but I'm not trying to solve that right now. What I'm trying to solve is the theory, okay? And we're working on the engineering, and I'll show you how that works. Okay, now, here's the only problem. I lied to you when I said that's all we need to do, okay? So yes, that's all we need to do to stimulate the input to vision. We have completely replaced vision. Here's the problem, that as Susan mentioned in her talk, a lot of what's happening in the brain is feedback. I disagree that feedback is more complex than feed forward. I'm going to digress for just 1 minute, just because I think you'd find this interesting. We published a paper in 2007, which we believe proved that the feed-forward connections throughout the brain, which are less numerous than the feedback connections by about 10 times, okay? That's trivial. It has to be that way if you're in a hierarchy, okay? So imagine you're going from the LGN to V1, okay? You've got center surround cells going to orientation cells that are feeding back. If the feedback from V1 was equally numerous to the feed forward, then all of the input coming back to the LGN would be oriented, and the LGN cells, when stimulated, would be oriented, okay? So if you're going to have feedback connections from V1 to the LGN, you have to have one for every orientation, okay? So that means in the thalamocortical feedback connections, you have to have 18 connections because they have a bandwidth of about 10 degrees. Okay? But they're only one lit up at a time. Okay? So now if you put a line in and you stimulate an LGN cell, and then you're stimulating a line in V1, and you're stimulating oriented cells that feed back to the LGN, only that orientation is actually stimulated from the LGN. So of the 18 feedback connections, you're only using one at a time. Okay? So the active physiological connections going feed forward versus feedback are 1-to-1. Despite the fact that the numerosity anatomical connections are more complex looking coming back. And that's something that the entire field of cognitive neuroscience, we think, ignored until we presented it in 2007. It's still obviously not well understood well enough, but I think that that's a proof, okay? I think that it's logically impossible to conclude that feedback is more complex than feed forward until you've solved you've shown that there's more feedback connections than you need to do things. Okay? All right. Moving on now. Yeah, sure. All right. So this, in concept, solves the problem of how we're going to do the stimulation. But we do have feedback, and feedback is critically important for gain control, for sure. That's at least one of the things feedback does, and to my mind, it's the only thing. Contrast gain control and attention, we now know neuroscientifically, are mediated by divisive normalization in GABAergic cells. And it's the same cells, okay? So attention and contrast gain control are the same neural substrate, the same mechanism, okay? Through feedback, okay? They may be activated differently by top-down versus non-top-down, but it's still the same tool that's being used. Okay, so how do we get feedback? Our prosthetic needs to get feedback from the brain that tells it how to change the power levels at all times in order to do contrast gain control. Otherwise, this isn't going to work. Okay, so what we do is in V1, we use the same genetic tools to make those cells not into photoreceptors, but into light emitters. Okay, we give them bioluminescence. Calcium comes into the cells. They light up like fireflies. And we can actually do this in a way so that they all have 5 different stochastically arranged colors that the virus is put in. We inject 5 different viruses with 5 different colored light, 5 different colored jellyfish, fireflies, etc. Okay? And then what happens is those stochastically infect cells, and each individual cell will be a random color. Okay, now if you put a color camera on the cortex, you can just detect the colored photons. And if you're looking at orange number 10,232, okay, you know those photons came from the same cell, because the likelihood of 2 cells having exactly the same color is less precise than even our best recording electrodes in terms of being single cell recording devices. Okay? So we're basically leveraging the same process we use to see color vision with 3 different cones with a 5-colored camera on the surface of the cortex. In fact, since we're only measuring the color, we don't even need a lens. Okay? We're just counting photons that come in and knowing their color. And now we can know hundreds of thousands of cells at a time how they're firing. Okay? Make sense? So now imagine this problem in terms of like the engineering is you need an implant that fits under the brain, that's non-percutaneous, it doesn't cost any, you don't have to have anything coming through the skin, okay? You can charge it from the outside using the same inductive coils that my iWatch uses to charge, okay? And it has a ultra-wideband connection to software, hardware outside the brain, like a camera that sends information in, okay? It has a video camera that has crappy, very imprecise pixels compared to that camera or that projector, okay? To stimulate, right? It's just laid up against the cortex, and we're stimulating those hypercolumns, and then it needs to receive the colored blinks of light that come out with a color camera. That's it. That's the solution to this. And you can now change the power as you go back in real time, in a real-time control mechanism, in order to have your contrast gain control. Okay, make sense? Okay. Easy. All right, let's take a look. It's a
Could you define, because you said it's the same mechanism of attention.
Yeah.
But I think contrast gain control.
Yeah.
Seems to be more general.
Contrast gain control, I would say, is an automatic process, but it activates the same inhibitory neurons and operates through divisive normalization that we now know from John Reynolds' work and other people's work is, and our own publication in 2008, we had a paper in Nature Neuroscience showing that divisive normalization is the mechanism of attention coming back into V1. So in V1 and V4, attention is divisive normalization. And those same neurons mediate contrast gain control, which I would say is non-top-down version of attention. But basically, it's suppressing everything but where you're paying attention. So if attention doesn't enhance any signals. There's no increase in signal to noise due to attention due to enhancing the S. you leave the stimulus alone and you suppress the noise from the surround to increase your signal to noise. And that's true for contrast gain control, and it's true for attention, and it's the same neural substrate to do both. Okay, make sense? You had a question? Okay, Clemens, right? Yeah. All right. Anybody have any questions about the basic? Sorry. Okay, did it.
Well, where does this map come from? This is learned?
No, we know the map. Oh, human weasel discovered the map. It's before him. Those yeah. So we don't. All we need to do is listen. Okay. So let's say we listen to. Let's say there was 2 colors, orange and green. Okay. So we just listen for orange. We know where the eye's looking. Okay. And through reverse correlation, for whenever an orange pixel comes in, we can see what's being lit up. So what we do with the patient is we basically just, after we implant it, we show them some white noise where we know the noise very well, and we can determine this. It's exactly the same way that we map receptive fields in the brain's mind.
So I was thinking they had to learn it, but you
No.
just
No, they've got their map.
get the map from
They've got their map. Now, this assumes they have a map, so we're talking about adults who lost their vision as adults after their critical periods. They have to have eyeballs in our scenario. So if you have traumatic injury, you lose your eyeballs, we can't track your eye position. Now we lose that aspect of this, and we don't think it'll work. Okay? So, but what this means is we take a blind person, they can't see, but we know from retinal prosthetics that once you turn on the prosthetic, they actually start having normal eye movements again. Okay, because they can see and their brain uses that information and starts moving the eye appropriately. So if we believe what's going to happen, and we haven't done it yet, but if we believe what's going to happen is that you take a blind person and you put this implant in, you turn it on, they're going to start moving their eyes in a normal way. Okay, and then we can track where their eye position is, and using the camera, we can know what part of the visual field they're looking at and beam that in based on where they're looking. And if they move their eyes, we'll beam in a different part. Okay, make sense? But we only have to put in a square centimeter of cortex. That's enough for the fovea. That's about 1/3 of a degree by 1/3 of a degree. Tunnel vision for sure, but definitely would increase the quality of life of the patient, and so it's worth doing. Okay? Okay. No, we did this already. All right. The basic idea is we have our hypercolumn, okay? We're going to stimulate artificially. If we stimulate two areas, the one part of one hypercolumn and the next, and say the black spot in one hypercolumn and the white spot in the next hypercolumn, that's going to be basically giving us the inputs to a small simple cell, okay? In fact, we now know this is what simple cells are. Simple cells are the neurons that happen to sit between these 2 inputs on the cortex, okay? So the neurons in the upper layers of cortex that sit between these two points are what we call simple cells, or complex cells if they're connected to the simple cells that are there as well, okay? Now, what we believe is that if we stimulate here and here, and we stimulate there and there, which is a simple cell that's in the next position over, and we stimulate here and here, which is a simple cell on the other side, that these neurons are connected with axonal connections, because we know that simple cells in the cortex in V1 have axial axonal connections that connect along the line of their orientation with their neighbors, okay? And they mutually recurrently feed back to each other. So we believe this is how you build a true simple cell in the cortex from other people's work. So we are now going to replace that by stimulating those 6 regions in order to stimulate what we call a simple cell. In reality, we just stimulate the same pattern that we'd have if they were seeing something in real life, right? And so if we can stimulate those neurons in the same way that would be stimulated in real life, then we basically have solved the problem. Make sense? So that decoding aspect is a different aspect of the research, but this is the, how do we, once we have that coding mechanism, we know the spatiotemporal kernel for each individual place as a function of the visual field, then we can basically restore vision. Everybody on board? Anybody not believe it because there's a huge flaw here? Okay. All right, so how do we do the LGN optostimulation? The entire talk. Okay. So this is our actual research, and this is, I think, where I started breathing. Okay, after years of work into this, okay, we've taken a monkey, we've injected optogenes into the LGN. They transduced, woo, okay, they percolated up the optic radiations to the boutons. The boutons now are sensitive to light. Now we've stimulated on the surface of the cortex with the blue light, okay? Those are the only thing in the cortex that are sensitive to light. There's nothing else there, okay? And with the spatial resolution that's within less than 100 microns of spread, I'll talk about spread a lot, okay? Because that's a potential problem with our idea, is that if light scatters in the cortex too much, we can't be precise, okay? But so we put a, I believe this was a 4 millimeter spot on the cortex, and we also transduced into the cortical cells a calcium dye that we could read out, okay? And we can see that we're getting a 4 millimeter calcium activation in the cortex. That means we stimulated the boutons, they stimulated the upper layer of the cortex, which then gave us a calcium signal that we could read out. That's it. This is gonna work. I don't know exactly what we'll have to change in jury rig to make it work in the engineering, but in theory, this can work. That's what this says to me, okay? We can do the prosthetic input, we can read out the output from that. It's precise. It's not just precise, it's very precise, okay? I want you to look at that. Looks like a bunch of noise there, okay? We did this experiment, I think 4 years ago. For 2 years, I thought this was a bunch of noise and I was just thrilled. That's not noise, okay? Let's talk about what that is. Okay, so here's the basic idea. We have our monkey cortex, we have our baseline, we stimulate with a blue spot because the channel rhodopsins in this monkey are sensitive to blue, okay? And we get that activation, okay? So, when we analyze this activation, maybe I can use this pointer. Can I use this spot? Oh, you were right, Juan, I was wrong. This does work. Okay, yeah. So here, that's the spot, okay? Now if we analyze these stripes, I noticed they were all in the same orientation, okay? They tended to run, and it turns out that on and off column stripes run in the same orientation. Are we looking at the on and off column stripes here, okay? So what we see here is if we analyze what's going on here in the black stripes, we basically find that they have a certain orientation and that they have a certain width in size. And that width is exactly what we'd expect to be part of a hypercolumn. Okay? Yeah,
How many hypercolumns are a monkey?
they have 1,200 total. Okay? And so what you're seeing here is about 5 hypercolumns given the size of this. Okay? So now we said, what about the white stripes? Okay, so we analyzed all of the white stripes and determined that they have the same orientation and the same size. Okay, and they're interpolated. Okay, interpolated. So we believe that these are the on and off columns that we're looking at here. Okay, and if we analyze these in terms of the population, we see that there's actually more black than white, and that actually is what we find. There's psychophysical evidence that black has a stronger signal than on signals. This is Charlie Chubb's work, and also that there are more off columns than on columns in the visual cortex. For some reason, we don't know. Okay.
Wasn't that to do with attention, what you were saying earlier?
No. This is off and on. This is just whiteness versus blackness. For some reason, blackness is dominant in terms of the number of columns, and it's something that is paradoxical. We have no idea why they're not exactly even, but we know it to be true already from previous research. Okay, so this is looking good. All right, now what about the scatter? Now I told you scatter is a problem. So if we shine a light, the smallest light we can do, and we shine it into the cortex, bright enough that it goes down 1 millimeter. Remember, the LGN boutons are in layer 4. That's 1 millimeter deep. Okay, we now have to model the cortex as a scattering medium. Okay, but this becomes a physical optics problem. Okay, so you have light and you're going into a physical medium that has scattering properties. How much power do you need to activate the channel rhodopsins, which require a certain amount of light to activate? And do you have to put in so much light that you kill the tissue, or before you can get down that deep, or can you get enough light down there without damaging the tissue that it doesn't scatter so far that it's useless? Okay, so we've done the modeling now. Okay, so first off, I showed you already that the spot we put on the cortex gave us a very precise output. That already, in a sense, answers the question. But let's be clear about exactly how much scatter we have, and does this theoretically actually make sense from the modeling, okay? So we built a model in what's called ZMAX, which is physical optics modeling software that physicists use, okay? And the idea is using empirical data from the Desimone lab at MIT, who actually used light measuring devices going deeper and deeper into cortex to measure the cortex as a scattering medium for different colors of light. For this color of light, which is red, we found that if we put a 16 by 16 micron LED on the surface of the cortex, which again is a huge LED from the point of view of your phone or your TV screen, okay, on your laptop, that if we put a 16 by 16 LED on the surface of the cortex, and it's at far less than physiological levels of damage for light, okay, what we get is that 16 by 16 spot basically spreads out to be about 100 microns wide when we get down a millimeter, okay? About 100 microns wide. Remember, we're shooting to be between 200 to 300 microns in order to be small enough to be perfectly isolated in one of the hypercolumns quadrants, okay? So we're well below where we need to be, but it's even better than that, okay? Because the spot that's bright enough to actually activate the optogenes is the yellow circle and the red circle here. So it's really only the radius of about 30 microns in the center of that spot that will actually activate the optogenes, okay? So we can be very precise. And not only that, if you consider this blue square to be the size that we're shooting for, okay, we can now put 72 of these spots in here. So we can not only control the amount of stimulation in the hypercolumn, or in the quadrant of the hypercolumn we want, with 8 bits of control, okay? But we have another 2 bits just from adding more spots to that area because we now have another dimension by which we can add more light. Okay, so now we actually have 10 bits of color and brightness control in our prosthetic. So when I say maximal contrasensitivity, I mean maximal contrasensitivity. This screen is 8 bits. So it's going to be 4 times better contrast control than we have right now watching this screen. Okay? In theory. All right. So let's model this. Okay. Turning on the sound now. Turn off the mic, please. Precision we need to stimulate just the neurons we want. And remember, in one of these places, any one of these places, if we hit any one of the LGN inputs or several of them, it's fungible. Okay? What I mean by fungible, it's like money. Okay? You can have money in your bank account and you can say, oh, I'm going to save money over here to save up for a car. But you don't really need to do that. That's just a mental construct. You could just have one bank account and have all your money in the one bank account and just use it. It's fungible. It doesn't matter what you spend it on, right? These neurons are fungible. They all do the same thing. They all represent, if I light up one spot of light over here, I'm going to see the dimmest star in the sky. That's the smallest thing I can see, right? If I stimulate the spot over here, I'm going to see exactly the same dimmest star in the sky in space. Okay? It doesn't matter I'm stimulating different neurons. They represent the same point in space in my visual system. Okay? Now, what happens if I stimulate both of those spots? Anybody? Twice as bright. Twice as bright. Okay? What if I did one spot, but I made it twice the area? Twice as bright. It doesn't matter. Everything I stimulate in here is going to be for that one spot, period. Okay? And then I can make the contrast vary by stimulating its off neighbor, okay, in different amounts, and I can control contrast. Okay?
1 millimeter depth is enough.
That's where all the boutons are. That's where all layer 4 is where that's where layer 4 comes in. The whole cortex is 2 millimeters. If we needed to go down to the bottom, we could. We now know it's just going to be, the scatter is going to be roughly twice, but it would still actually be precise enough. So we can go all the way through the cortex if we want to. We don't need to. We only need to go halfway down. And this is going to work with regular LEDs just sitting on the surface. We can just use a micro LED array using super cheap LEDs. Now we're not going to use super cheap LEDs. There's reasons for that. I'll talk about some of the advanced photonics we're developing for that. Okay? All right. So here's how we actually do it. Here's the largest 2-photon image that's ever So it's not just a theory, okay? We can do it. We already knew, we can make neurons that have a brain bow, right? That's been achieved. That's been solved by people, smarter than us. We stole their techniques and we used them, period, okay? But instead of putting in fluorescent dyes of different colors, we put in bioluminescent dyes, which is not different. Fluorescent dyes actually came out of bioluminescent animals. We took off the bioluminescent part. We just and used the fluorescent part for fluorescent dyes. So now we're just using a larger part of the gene and we're making them all bioluminescent, okay? So this works. We can now read it out in color, okay? We did it, okay? Okay, so let's look at this. So if we now look in our 4-channel 2-photon microscope for different colors, we can see these are all 61,000 cells and their preponderance for with signal-to-noise ratio as a function of cell count for how red they are, and how yellow they are, and how green they are, and how blue they are. Now, you can see that because of the signal-to-noise level differences for these colors and the preponderance by which they transduced, we have different numbers of levels of the different colors. So what we did is we said, okay, if we just looked at one signal-to-noise level versus the other, which is we could have done, it's possible that we'll accidentally look at the same cell twice, okay? But what engineers have done to address this issue, it's just a rule of thumb in engineering, is you group these into 3 levels of 3 signal-to-noise ratios, okay? To know that you're looking at 2 different signals, okay? So what that means is we have 27 levels of signal-to-noise in the red channel that we found. So that means if we take a picture of all the redness in that image, okay, there's 27 different levels of redness, okay? But what we said is we're just going to count the cells in groups of 3 levels at a time. So we have 9 different levels now that we're going to count. And we know that each one of these different levels are different neurons, okay? So it's a conservative, we're underestimating the number of neurons we're looking at by a lot, by 3 or more, okay? So now we do the same thing with yellow. That's a brighter dye. We have 11 levels. We have 7, I think, with green, 8 with green, and we have 6 with blue, okay? So that means the number of colors we can measure is, maybe that's on the next graph, but if we look at the cells there, are we just looking at a bunch of super dim cells that we can't see, or are we able to really look at these cells because they're not just up against the signal-to-noise barrier at threshold, okay? And the answer is that even if we don't count this bottom level at all, most of the cells, especially in the blue channel, are in the realm where we can actually look at a cell and see how much red, how much yellow, how much green, and how much blue. So how many different colors could we have, right? How many different colors can we have with this, okay? Well, just using this, first off, we can see I believe it's 4,912 is the number of colors that we can measure, okay? And if we look at these 61,000 cells in terms of their actual, where they lie in the color space, you can see it spreads the color space very well. Red is really weak in general compared to the other colors because in our 2-photon microscope, when we did these experiments, we had a red filter on because we use we're using red light for the 2-photon aspect of this, okay? So we're actually tying one hand behind our back in terms of the redness, okay? But the point is that it spreads the space evenly. That means that we have at least 5,000 different colors we can use to measure these cells. Now that's 60,000 cells we measured. That means that in the entire 3.14 centimeters square of cortex we were looking at, okay, there's only 12 cells of each color, okay? The likelihood that any 2 of them are at the same position and that we're misinterpreting the color that we read out as being for 2 different cells that happen to be at the same position is far less probable than measuring 2 cells at the end of one electrode and misinterpreting that, okay? This is a true single unit recording system, okay, you got it? So we should be able to do, in a human being, with this NV1, single unit recordings, okay? That's the idea, all right. All right, so how do we do it? Now, I told you before, we're going to use LEDs and a cell phone camera. That was my original idea. And I took it to my friends at SUNY NY Creates, which is the largest publicly held photonics fab in the world. And I said, this is what I want to do. Can you make me one of these chips? And they said, why would we do that? Let's just use photonics. It's cheaper, it's more efficient, and all in all, just better. So we make a neurophotonic thing, which I didn't know existed. Let me show you some of these things. It's like science fiction. All right, so the idea is this. You've got dyads here. So the black thing is the emitter, where light comes out, and it'll be at just the right color to stimulate those LG and photons. And then you have a 5-color camera right next to it. And because the spread of the light is as low as we say it is, we know that whatever this activates, the light coming out of the brain will only stimulate this one channel. These are spaced in a precise way that none of the light we stimulate here is going to activate that camera. Okay? It just doesn't scatter that far. That's what the modeling shows. Okay? So these are isolated channels. Okay? And then if we dive in there, this is the diode I was just looking at. You can see there's a couple elements here. There's something called a Mach-Zehnder interferometer. That's this weird thing here. And then there's a magnetic ring resonator. So the idea is this. A laser light comes in through this fiber. Okay? The micro ring resonator, if you put power on it, it changes the optical density in just such a way the refractive index changes, and light can transfer through a quantum process into this fiber. But it can't get through without that. So we're turning on and off the light into this channel with this magnetic ring resonator, which then travels down, and we can use other magnetic ring resonators to send it down to different channels. And then we can use a Mach-Zehnder interferometer, which takes the light, splits it in half, sends half of it through that channel, half through that channel, and using an electrical input, changes the optical density of just one of these, just enough that it will actually change the phase by 1/2. And so you turn off the channel right there as well, okay? And so we can 8 bits of control. And when it hits this emitter, the light makes a 90-degree turn and comes out, okay? So using these photonic tools, we can control the light very quickly and very precisely. It looks something like this. There's a little sound here. You turn off the mic, Alex? Bada boom, bada bing. That's it. Okay? So they tell me that they can make these things easily, that this is like child's play type of photonics. Everything we're talking about is so big compared to what they're used to do telecom stuff. Okay? That human circuits are just super primitive compared to what they're doing for what they developed these tools for. Okay? All right. So just some more of, so this is actually a picture of what the colored photons look like in the bioluminescent cells. This is a cortical picture, and this is what the cortical cells actually look like. It's a 2-photon micrograph, okay? And then we need a 400 by 400 camera with each one of these pixels would have an LED in it and 5 micro cameras, each with a different filter on it, okay? Or we can use the photonics I just showed you, okay? And then we would have 8 bits of information going in to control the pixel for each point. And we would have 8 bits out for each of the cameras coming out for each point. They just are on or off at 8 bits. And we build an image from there. And then we need a communication system that has power and can communicate basically through ultra wideband up to 480 megabits in those channels, because that's your limit with ultra wideband. But the bottom line is the engineering all works out and you can do it, okay? So with the input data and the output data, 400 by 400, you can do it with just the same technology that is in my phone right now. Okay? Yeah, question.
In the case with the infection with the virus, how long it lasts the expression of the channelography. So it is necessary because it's not an infection directly in the DNA. It's
It is. So it's an adeno-associated virus. We use AAVs, so it is directly into the DNA. So the transgene that we're putting in actually transduces into the nucleus and is put permanently into the cell. So it's there forever until the cell dies. So the cell becomes a photoreceptor from now on, forever.
So in this case, this technology will approve. It is necessary to do injections constantly.
Oh, and revise it later. No. And remember, the implant doesn't enter the brain. There's nothing entering the brain. There's no gliosis, right?
No, but I mean,
No, I'm talking about another issue. I know what you're talking about. You're saying, do we have to revise later with more injections of optogenes in order because the dye is going to wear out? No, because it's permanently put into the genome of the cell. The cell, as long as it's alive, is going to make the dye because we put it with the promoter of the same promoter that makes the transmitters in the cell. It's a synapsin promoter. So whenever if it's a neuron, it's gonna become a colored cell. If it's not a neuron anymore because it doesn't make synapsin, then it's gonna not be. But it's not a neuron anyway. Okay.
Epigenetic phenomenon can shout the expression, but it's an promoter. It's not the case. So because
All right.
You
Yeah.
have 5 more minutes.
Oh, thank you. Did I use the whole hour now? Okay, thank you. So I'm almost done. So here we have what it actually would look like in a human. So we have we didn't talk about the technical problem of building the implant itself, which was quite a problem. It took us a few years. But we can basically do this with printed technology, and we developed a new kind of silicone that will allow us to hold this against the brain without damaging the brain at all. And of course, it doesn't enter the brain at all. It doesn't ever cross the pia. The pia is intact. So there's no degradation of the brain itself. Okay. So that's kind of what it'll look like, and that's where it will go. And the whole system would include the glasses, the eye tracking glasses, and presumably something like a cell phone to mediate between these two systems. That's a problem for someone else. Okay, these are my friends who helped me get this far. Thank you very much.
Thank you very much. We have time for questions. Bueno, primero vamos a ceder, ver si alguien que está en línea tiene alguna pregunta. Sí, pero vamos a otorgar tiempo a ver. Vale. Muy bien, iniciamos, doctor Juan.
Well, thank you very much.
A lot of information give us, and it looks amazing and very clever, and I think very needed. However, I would like to address something that runs parallel to your own research, and it has to do with research that was done by Paul Bajirita on sensory substitution, and on the other hand, what Oliver Sacks talks about blind people, having restored, their vision, and the traumatizing experience it can mean. Because we seers consider that vision,
Most novel,
like Descartes would say, of the senses, but what about someone who has lost sight or was born, blind? Is there a program that you can think of that would come along? Because Oliver Sacks talks about this guy Virgil, who ended up killing himself, right, because of depression or whatever. So restoring vision, do you think it should be accompanied by some kind of pedagogical or therapeutic accompaniment? So there are two questions, whatever you want to react to. Sensory substitution. I know it's very gross, I mean, compared to this, but Bajirita would say that it was good enough. They could read with the skin. They could read headlines, in the newspapers and so on.
If people want to use sensory substitution instead, it's fine. I mean, I don't have any concern with that, but I think restoring vision at the level of 20/20 vision is a different goal, and I think that is just a fundamentally different thing. So I'm not going to address that. The issue of the problem with people actually not knowing what to do with the new information they're getting from this. So our system is designed for adults who went blind, okay? So presumably they want to not be blind anymore, okay? But they already have the maps in place that they developed through normal processes. They went through periods. And now, so we're restoring lost vision in an adult, okay? So that's not to say that issue is completely addressed, but I'm also just going to set that off with being, I'll solve these problems. Let Oliver Sacks's friends solve those problems. I can only do so much. But to not be too jocular about it, okay? If this works, there's no reason you can't make it smaller, okay? In theory, this engineering is done by a neuroscientist who knows nothing about engineering, okay? Now, I've checked it with engineers, and it holds up. There's nothing wrong with what I did. But it's also very crude, okay? A real engineer who could presumably make these things much smaller, and we could solve other problems, like instead of having this be a hard disk that connects to the bone underneath, it could be a film that actually would allow you to cover the entire V1 surface, even though it's bent around corners and things like that. And maybe if you could do that, you could put it in a baby's brain who was congenitally blind, and then we wouldn't wait till they were adults to put this in because they wouldn't have the maps. They would have the maps because they'd have a normal visual process growing up with artificial eyes, okay? That would be the idea. And in fact, you don't actually need the goggles here. So I said here that we would do eye tracking with these goggles. It's almost certainly not the case. This makes it easy to understand. But it turns out that we now know that you can do very precise eye tracking. In fact, the most precise eye tracking I'm aware of is actually done with an electrode array in the frontal eye fields. Okay? So if we had a second implant over the frontal eye fields that just read out the frontal eye fields, we probably could do all of the eye tracking inside the brain without having to do anything in terms of glasses or anything, which would mean this would be a viable choice for a baby. Okay, and they don't need to know how to use the system. Okay, they would just use it just like they use their own system now that they don't know how to use. Right? Make sense? Okay. Anyway, I hope that answers your question. I'm sidestepping a lot of the emotional issues there because that's my prerogative. So.
Yeah, thank you. Just very quickly, I didn't understand how the feedback forward mechanism works. Could you just clarify that?
So the cortex, we've put in bioluminescent genes to make the cortical cells flicker like fireworks when they activate. So when calcium comes into those cells, they light up just like a bunch of rainbow fireflies. Okay? And then we have a color camera that reads out the colors. It doesn't even have a lens on it. It just counts colors. And because each cell is a different color at a given location, under a given color pixel, the likelihood of there being two cells with exactly the same color, okay, is so close in color that we can't tell the difference is virtually zero. Okay, it's very low. Okay, it's not very unlikely, put it that way. So we don't even need that. Okay, what we need to know is in a given how much power do we need to put in the next pulse in order to keep up with the contrast gain control, okay? So the idea is we stimulate and we get feedback. But the cortex is constantly changing, okay? It's constantly changing because the patient drank some coffee, the patient is sleepy, the patient is in different light levels. Okay, all of these things are constantly changing the cortex. We know from the motor prosthetics that have already been made, motor and somatosensory prosthetics, that you have to have a real-time control loop in there that's constantly feeding back the contrast gain control. You have to read out the neurons and then stimulate. Read out the neurons. If you just stimulate, nothing works. You just can't model a single stimulation level. You have to continually turn it up and down based on how the brains are reacting to, for one reason, because if you stimulate the brain, it's going to stimulate differently to the next pulse that comes right afterwards, for sure, just due to adaptation. So the timing of your pulses affects this, all of this. So you're constantly reading in and reading out, and then changing your stimulating in part, or your writing in. The reading out is done by a color camera reading out the flickering fireflies in the cortex. The writing in is done with a laser-based light pulse that stimulates the LGN photons. That's a different color. It's in a different domain of color, so they don't interfere. Yeah. Let's shoot for 60 hertz. That's what we're looking at. 60 hertz. And you want to speed it up from there? That's a manufacturing commercial issue. That's not mine. I'll do the theory. Okay?
Vamos con una última pregunta de este lado.
Very engaging talk, very interesting. I was thinking if you could say something about what we were talking yesterday, that on the basis of this approach, healthy people we could build for healthy people cells that are sensitive to new aspects of the wavelength, and we have these superhumans able to see in the dark and things like that. If you could say something about it.
Fundamental question why I thought it would be appropriate to talk about this in a cognitive neuroscience. This is a very low-level visual issue that I've been talking about, and a cognitive neuroscience. So why am I doing that? Oh, the point is that if you knew the thalamocortical inputs to whatever cortical area you're in, it would work. We don't need to know the map. How are we going to map? How are we going to know that our lights are in the right position to not stimulate two channels at once? The answer is very easy, okay? If you stimulate, okay, and you get out two light pulses, two different positions, you know you're at the border. If you stimulate and you only get light back out from right under where you put it in, you know you're in the middle of the channel, okay? So we don't actually need to know the map at all, okay? It's just gonna work, okay? The brain then uses that information, period, okay? So then, yes, we need to actually we need to find out through measurements where in the visual scene that specific point is in the visual scene, but we can do that from just letting the person look at the scene while we measure the scene with the camera, and then looking at the output, we just do reverse correlation and we determine the receptive fields of our input-output system, which is exactly how we determine the receptive fields of a monkey's neuron in the visual cortex anyway. We just show it white noise, and we know where it's looking, and we can determine exactly where that receptive field is and what kind of receptive field it is based on that. Okay? So that's the basic idea. Yeah.
How long it lasts this?
But hold on, I didn't quite answer his question. Not quite yet. I want to finish answering. So the question you have, how does this relate to, could you use this in a normal person, right? In a sighted person, I should say. Yeah. So the answer is you can use it outside the visual cortex. There's no reason you couldn't, okay? And as long as it had a map, okay, it should work. We don't even need to know what the map is before we use it, because we find out after the fact. And in fact, when you install these things, it's not like you'd map the cortex and put it in a very specific place. The surgeon would just put it in. We'll find out what the map is later. We just need to know roughly that it's over where the fovea is, which is done by phrenology, okay? We just know that before we go into the brain, that the fovea is going to be right under the operculum of the skull. That's it. It's going to work, okay? So now the issue is, can you use it in a sighted person? Yeah. There's no reason stopping it. In fact, the way I got interested in this is there was a huge DARPA funding cycle where they paying $60 million to a group who could develop something like this. And I was like, I like money. So I started thinking about this. And I'd long thought that electrodes were never going to work and it was a waste of time in prosthetics. But it was around that time, excuse me, sorry, one of my family members is calling me. It was around that time that optogenetics became a thing. And around that time in 2016, that the map of the LGN inputs to V1 happened. When I saw that paper, I knew immediately that you now don't need to use electrodes. So that was, I think, my only real insight here, personal insight, was like, okay, this is now solvable, okay, because we know the LGN inputs to V1. And so, so the question is, why is DARPA have this program? DARPA isn't trying to cure blind people. Okay, they're not doing this program because they want to cure patients on the battleground who got traumatic ocular injury. I wish that were the case, but they had other things in mind. Okay, and so yeah, they're trying to make super soldiers, I think, and trying to make televideo systems. And there's no reason that the camera that's controlling this would have to be visible light camera. It could be infrared. It could be all sorts of crazy shit. Okay, so anyway, but yeah, I think Elon Musk's fundamental interest here. I've never heard him say he wanted to restore vision with Neuralink. What I've heard him say is he wants to play Spotify in his brain, right? And he wants to be able to think and control Siri. So that's what he says. Okay.
Thank you very much, Dr. Steven. We are glad to have you here. I'm going to give you this recognition for you. And
thank you. How nice.